Okay, this example is a little bit of a puzzle. We're looking for something where the limit exists, but the function at that spot does not exist. You can see when x is -6, the limit exists as x goes to -6, but the problem is the function also exists, and that's not what we want. The limit does not exist at -4. It also does not exist at 2. But here's a good spot. When x is 5, you can see that the limit exists, but the function at that spot does not exist because there's no point there. So the c value is going to have to equal 5. Okay, here's another puzzle that we're going to look at. It's kind of another example of a removable discontinuity. Here it says that the limit exists. So let's see, the limit exists here, and the limit exists here. It also says the function exists at that spot. So we can look at this spot here. And it says it's not continuous at that spot. So -6 is going to be our answer. If it said that the function was continuous, there would be an infinite number of answers. All of these spots would be answers. So the answer to this puzzle is going to be x equals -6, or in this case, b equals -6. Okay, we're going to quickly review the types of discontinuity. The essential discontinuity is when at least one of the one-sided limits does not exist. So that's usually an endpoint, or it could be a vertical asymptote. A jump discontinuity is where the function jumps. So you can see that both of the one-sided limits exist, they're just not equal to each other. That usually happens with piecewise functions. The most common one is the removable. The removable is where you just have a hole. You could have a hole with a point, or you could have a hole with no point. They're both considered removable discontinuities. And according to the AP test, everything else is considered non-removable. So a jump is considered non-removable, and so is essential. So it's a little bit easier when you're taking the AP test. Now here we have to describe the type of discontinuities that we see. There's going to be a hole here. A hole is a removable discontinuity. And this is going to give us a vertical asymptote at x equals -1. So that's going to be an essential discontinuity. Okay, if we were going to sketch this, you can kind of see there's a hole when x is 2. So that's going to be your removable discontinuity. And there's a vertical asymptote when x is -1. So that's going to be your essential discontinuity. Okay, we have a piecewise function here. We're going to start when x is less than 1. We have the function x squared. So we're going to want to leave an open circle when x is 1, and then we'll connect our dots. And we're only graphing it when x is less than 1. Okay, when x is equal to 1, it's at a height of 2. And then when x is greater than 1, we have this line, 3x minus 2. Again, you always want to plug in the endpoint of 1, and that would give you 1. So you can probably see that we have a hole, even though they connect, we still have a hole at x equals 1. So what we end up with is actually a removable discontinuity when x is 1. Okay, for this example, it's going to be x squared when x is less than or equal to 1. So that's going to be this part right here. Okay, then it's going to be 3x when x is strictly greater than 1. So y equals 3x, just a line. But you start when x is 1. If you plug in a 1, you get 3. So that's where you're starting, and your slope is 3. Okay, after drawing this, you can see it's asking for any type of discontinuities. It looks like there's a jump discontinuity at x equals 1, and that's because the limit from the left exists, the limit from the right exists, but they're not equal to each other. So we have a jump discontinuity at x equals 1. Okay, now we're going to take a look at the intermediate value theorem. We only have about 3 theorems that we're supposed to know, and this is one of them. The intermediate value theorem says that if your function is continuous on the closed interval, then it's going to take on all the heights from the beginning height to the ending height. The way that we use it is, let's say the beginning height is 2 and the ending height was -3. So we're saying that this function is continuous on the entire interval from x equals 1 to x equals 5. So that means the function, we don't know, it might go up, it might go down, but but it's continuous, so we're guaranteed all the intermediate heights. So we're guaranteed every height from 2 all the way down to -3. Now we don't know if it goes up, so we're not actually guaranteed any heights above 2. It's possible that the graph might just go straight to the other point. But we are guaranteed every single height between 2 and -3. So we're guaranteed a height of 1, at least somewhere inside that interval. There's at least one spot where the height is 0. There's at least one spot where the height is -1 and -2. So we're guaranteed all intermediate heights. Now the way that we usually use this theorem is we can usually guarantee that there's a 0 if the original height was positive and the ending height was negative, because we're guaranteed all intermediate heights, and 0 is an intermediate height. So that's how the intermediate value theorem is usually used. Okay, now we're going to do an example of using the intermediate value theorem to show that there's a 0 for this function in between x equals 2 and x equals 3. Our first step is we must say that the function is continuous from 2 to 3. And the reason is because it's a polynomial, and polynomials are continuous everywhere. So now we want to check the beginning height and the ending height. Now if you look at the graph, I'm going to try to explain it. The beginning height is -2, and the ending height is 12, which is actually off my graph paper. It's way up here. And because this function is continuous, you can't go from negative to positive without going through 0. So we're guaranteeing there's at least one spot where the y value is 0, and we don't have to say where that spot is. The intermediate value theorem is just an existence theorem. So we want to write out our final answer. We're going to say, so by the intermediate value theorem, and I'm just abbreviating it, there exists at least one spot, we're calling it C, that's inside of that interval from 2 to 3, such that f of c is 0, which means the height is 0, the y value is 0. Okay, for this example, they're telling us that the function is continuous. So if it's continuous, then all the points must be connected. Now, I've already plotted all the points, and now we're just going to connect them. Now, based on this picture, we can see that there's 1, 2, 3, 4. There's at least 4. So that would be my answer. Now, there could be a lot more than 4. Let's have a look. We don't exactly know what the function does. It could come down, it could come back up, could come down. It could cross through the x-axis many times, and we don't exactly know what's happening. But if you look at our previous picture, we know for sure, because it's continuous, that there must be at least 4. There could be more than 4. This could be happening. 1, 2, 3, 4, 5, 6, 7, 8, 9. This one has 9. But we're looking for the smallest amount of zeros that must exist. And so we're just going to connect the dots with straight lines. And so in this case, we're going to say, well, at least 4. All right, this is our last example. This is the extreme value theorem. Remember, we only have about 3 or 4 theorems the whole year. This is the second one we're learning in the same day. So extreme value theorem is actually the easiest theorem of all. It says if your function is continuous on any closed interval. So let's look at an example. Say we go from -3 to 5. We're not sure what happens, but let's just draw anything. So our function must be continuous from the beginning to the end. So you have to be able to draw the entire picture without lifting up your pencil. As long as this one thing happens, then you're guaranteed to have a max and a min on that closed interval. Now for this example, it looks like the max happened at the end point. It looks like the minimum happened somewhere around 2. And that's it. That's how easy the extreme value theorem is. Remember, an extreme value is like a max or min.